Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 34th lecture on sampling-based motion planning. All right, so let's get started with a video. Now, this is a video of modular robots. Modular robots are small robots that can self-assemble into larger structures. Maybe you could imagine a fleet of these modules coming together to build a bridge. Modular robots present a motion planning problem at multiple levels. At a high level, I'm thinking about my overall shape and what sort of shape I want to build in order to do some meaningful task. At a lower level, I need to plan the motions of each individual block, making sure those blocks come together to assemble this larger structure. And so in today's lecture, we'll be thinking about motion planning. I want to focus on the RRT algorithm. We'll talk about how we implement this algorithm and also how it compares to trajectory optimization. All right, so let's set the stage for motion planning. The main idea in motion planning is trying to come up with a path or a trajectory that will move my robot from some initial position to a goal position while avoiding any obstacles in my space. Now, it's just a plan, so I'm actually going to have to use my controller to make the robot physically move along this motion and perform this task. But I still need to come up with that plan for my controller to execute. And we've been thinking about different ways of coming up with these plans. In the last lecture, one idea that we had was an exhaustive search. And what we did is we took our environment and we discretized it into a set of cells. And then we tried to use a search algorithm to find the shortest path from the start to the goal. We saw that this was feasible for low-dimensional spaces, but it did not scale well to our serial robot arms. It became very inefficient. And so we changed perspective, and instead of having an exhaustive search, we focused on sampling. And the idea here is that we're going to sample random joint positions and see if we can find a path just using these sample positions from my start to the goal. So I'm not going to have to check every possible joint position. I'm just going to be looking through these sampled options. So how do we sample? How do we assemble them together? Well, that's what we're going to talk about today. And the first thing we need to understand is this graph. And this is going to be a data structure that we use when we're trying to find these paths from our start to the goal using the RRT algorithm. So at a high level, a graph is just a connection of nodes and edges. And I've got some images here on the right to illustrate this point. Here's a node, and a node just contains information. In our context, each node is going to be a sampled joint position. So this is a joint position my robot could move to. And then an edge just connects the nodes. In our context, it's telling me that I can move from this joint position to this joint position without having a collision. All right, so that's a graph. Now, for the RRT algorithm, we're going to look at a specific type of a graph called a tree. Again, it's going to have nodes and edges, but it has a very specific structure. For a tree graph, there is one node that's at the root of the tree, and that's going to be this one right here. In our context, that'll be theta start, the starting point that I want to have my robot begins there and then goes towards the goal. So this will be theta start. Every node besides the root has one parent. So here's my root. It does not have any parents. And then node 1 is going to be the parents of node 2 and of node 3. And that means in our context that I can move from theta start to either theta 2 or theta 3. Node 3 is the parent of node 4, so I can move from 3 to 4 without having a collision. Parents are just edges, and they're telling us how the nodes connect in a way that avoids collisions with the obstacles in the environment. So let me show you how you can implement one of these nodes in MATLAB. So I'm going to focus on this node, theta 4. For the examples I show you in this lecture, we're thinking about motion planning in an XY plane. And so all my joint positions are just going to be two-dimensional, X and Y. And so the first thing I'm going to declare is the position or the coordinates that I want to assign to this node. So for my node theta 4, I'm assigning the coordinates X, Y. And for this example, I picked 0.9, 0.7. Again, just some coordinates that correspond to where this joint position is. So that's part of the node. The other part of the node is its connection, its parent. And that's going to be, in our graph, the parent is node number 3. So I'm going to declare that the parent of theta 4 is 3. And these are the two lines I need to declare this node in MATLAB. Now, what that's going to be is a structure. So if I just print this off, it's a structure with two different fields, and you can see the coordinates and the parent. Great, so that's how you build one of these nodes in MATLAB, and we're going to try to connect these nodes to make our tree that we need for RRT. All right, so how do we actually implement this? First, I just want to start off with a high-level visualization. Again, we've got a root, that's going to be the base of my tree, and my tree spans out to cover this space. I'm looking at all these different edges that are connecting different nodes, so they're kind of telling me the parent of each individual node. And I'm also noticing that all these different nodes are in free space, and the edges show me valid motions that I can have that avoid collisions. Over time, I'm building out this tree until eventually I find a node that's within some radius of the goal. Then I can work backwards, tracing back through all the different parents until I get back to the root. And that's going to give me a path that goes from the start to the goal while avoiding collisions. Okay, so that's the outcome, but how do we actually implement this algorithm? I want to go through that step by step. On the left side, I'm going to show the kind of like the high-level intuition or the pseudocode. Now, this is what we covered in the last lecture. On the right side, I'm going to show you the actual lines you can use in MATLAB to implement the RRT algorithm. Okay, so at the beginning, we're going to initialize our graph with our root. And we've said that our root is going to be theta start. That's the starting point of my motion plan. And that's exactly what I'm doing on the right here. With my first two lines, I'm declaring that I'd like to make a node called theta start. I've given it some coordinates, and I've declared that it does not have any parents. Again, because it's the root of my tree, it does not have any parents. And then finally, I start a graph, and I say the first node in this graph is going to be theta start. Now, in terms of the dimensions here, I've got a two-dimensional coordinates because I'm thinking about something in the XY plane. If you have a robot with n joints, then this would be an n-dimensional vector, again, where you're declaring your initial joint position. Okay, the next thing we're going to do is we're going to enter our while loop. And you can write this as a while loop or a for loop, just depending on your implementation. The idea is I'm going to have a loop, and I'm going to go through n iterations of this loop. N is going to be the maximum number of samples I'm willing to have before I give up and declare failure. I can't find a path from the start to the goal. So N is our planning budget. At every time we go through this loop, the first thing we do is we sample a random joint position. And here I am sampling that joint position. Now, in the problem I'm looking at, and I kind of visualized it a second ago, we have a robot that's moving in the XY plane in a square between 0 and 1. So my joint space is any values for x and y that go between 0 and 1, and that's what I'm sampling from right here. If you had some other joint space, you would just set that joint space and sample uniformly at random from that designated joint space. Okay, so I've sampled a completely random joint position. The next thing I want to do is I want to look for theta near. Now, this is the node in my graph that is closest to theta rand. And this is going to be a search where I just go through all the nodes that are currently in my graph, and I figure out the distance between each of those nodes and theta rand, and then I choose the closest one. And here I am implementing that search in MATLAB. I start off by declaring the distances are all 0 because I need to fill them in. I don't know what the distances are at the beginning, but I know this is going to be a vector of length g because I've got I want to go through all the nodes that are in that graph and check how far each node is from the sampled position. And here I am going through all these nodes, and I want to update my distance vector. And what I do is I take that node jdx, and I get the coordinates of that node. So this period coord is just sampling out, pulling out the coordinates of that node. So I'm getting the xy position, and I'm looking at the distance between that xy position and theta rand, which is this random position that I sampled. Again, I keep talking about x and y just because that's the example I'm showing you, but it could be an n-dimensional vector for whatever your joint space is. So I check that norm, and I see how far they are apart, and I update my distance vector. Once I've completed this for loop, I now know the distance between every single node and that randomly sampled joint position. I then choose the element that is closest to, that has the minimum distance to theta rand, and that's going to be theta near. So I can pull that index from my graph and say, all right, this is the one that's closest to that sample joint position. The next thing I want to do, and this may not be intuitive, but I want to explain as we work through it, is I want to take a step from theta near towards theta rand. Now, you might be thinking, why don't I just go towards theta rand or see if I can directly connect theta near to theta rand? There are a couple reasons why we don't usually do that. And one of them is that theta rand, it could be any point in my joint space. So it could be really far away from theta near. And that would mean I'm trying to make this very long connection, and it's pretty likely that there's some collision between these 2 points. And I don't want to waste my time trying to make these connections that are really unlikely. And so I'm going to restrict my robot to only looking at points that are within a radius of delta from theta near. And so I'm going to be trying to find a closer point that still moves in the direction of theta rand, but is just closer to what I already have in my graph. And here I am implementing that concept. So first I take a vector that's pointed in the direction of theta rand. So I've got my theta near coordinates, they're xy coordinates. I'm just looking at a vector that's pointing towards theta rand. And then I check the length of that vector, the distance. Now, if the distance is less than delta, great. I can set theta nu as equal to theta rand. And so I build a new node with coordinates that are set equal to theta rand. If it's beyond my radius that I'm willing to work with, and it's like, hey, this is too far away, I don't want to try to make this connection, what I'll do is I'll just move in the direction of vec2 rand by distance delta. And that's what's going on right here. So I'm building a theta nu that moves from theta near towards theta rand with length delta. Okay, so I've got this theta nu. And the next thing I want to do is I want to check and see, is this new point something that I can add to my graph? Is this collision free? And the exact form of that collision checking is going to depend on your environment, but I've shown a very simple implementation over here on the right. I'm just going to assume that all my obstacles are circles or balls with some radius. And so I've got the center and the radius. And so all I'm going to do is just check those coordinates and see how far away they are from the center. If they're within this radius, there must be a collision. And if they're outside that radius, they are collision free. Again, this is a simple way to do collision checking. It won't work in all scenarios, but it's a good place to start. So I perform this check and I look at the distance between theta nu and the center of my circle. If it's too close, I've got this continue command. And what that means is I'm going to stop right here and jump right back up to the top of my while loop. But if I can pass this check, then I continue down my process. And the next thing I do is I add this theta nu, which is valid, to my graph. And I declare that the parent of theta nu is theta near. That means that there's an edge moving from theta nu to theta near, designating, hey, this is a feasible motion I can do that doesn't have any collisions. So in my implementation, I say that the parent of theta nu is equal to theta near index, which is just the index of theta near. And I then update my graph to include theta nu. All right, so I'm going to repeat this process. And at some point, I want to check and see, have I found a path from the start to the goal? So here's my stop condition. And what I do is I check and see if theta nu is close to theta goal. So if it's within this radius of epsilon of the goal, I've made it. I have found a connection or a sequence of nodes that are connected that go from the start to the goal, and I can stop my motion planning process. Now, you might notice I've got this end here. That just means the last node in my graph. And so I'm just looking at the very last node. Is this close enough to the goal? And we'll be checking this each time we add something new to the graph. So I'll be constantly checking to make sure that these new nodes are either not completing the task or they're close enough to the goal that we can complete the task. All right, so if we've completed the task, we return success. If we do this n times and we never are able to find this node that's close to the goal, then we're going to return failure. Okay, so that's the implementation of RRT. And if you'd like to test this out yourself and see what it looks like, I encourage you to go through the practice set. You can find it in the description or the pinned comment. The first page has the questions and the following pages have their answers. I've also got some code, again, so you can try this yourself and see how it works. So how is this going to compare to trajectory optimization? And they both have strengths. I'm not trying to say that one is better than the other, but they have some strengths, and it's worth understanding the advantages of these two methods. So the advantage for RRT is that it is probabilistically complete. I mentioned this briefly in the last lecture, but what this means is that the probability of finding a trajectory from the start to the goal increases towards 1 if there is a valid path, as the number of samples go towards infinity. So if I go through this RRT process enough, and if I keep sampling enough random points, eventually I will find a valid path if one exists. This is not the same as complete because it's probabilistic. Like I might take a lot of samples and fail to find a path even though there is a valid path. Overall, though, this is a pro as compared to trajectory optimization. You might remember that with trajectory optimization, we can get stuck in local minima, and that's not something that's going to occur here. The downside is that the trajectories we get are not really smooth or optimal. When we were doing trajectory optimization, I was optimizing for some loss function, and I was finding trajectories that minimize that loss function. Here is a pretty stochastic process, so I can get these jerky trajectories. But I like to show this example on the right as a great example of success. Again, I'm in this XY space. I've got these two large obstacles, and there's a very narrow path between those obstacles that I need my robot to find. I would have guessed, if I'm just thinking about this naively, with random sampling, it's going to be very tough to find this path between these obstacles. But actually, if you kind of watch this again, the robot is able to find it pretty quickly. And so I just think this just shows that the RRT algorithm might be more powerful than you first think when you're looking through the code and thinking about random sampling. Okay, so I've already mentioned the practice set, and I encourage you to go through that. That'll help you understand how you implement the RRT algorithm, as well as how the RRT algorithm compares to trajectory optimization. And with that, I'd like to end this course. I hope you found it enjoyable and informative. We've covered a variety of different topics in robotics. And now that you know this information, I encourage you to continue your work in robotics, wherever that might lead you. And I look forward to seeing the outcomes that you generate within the robotics community. So thank you, and see you again.